Okay, before we get started doing any hypothesis testing with variances and standard deviations, I want to review some of the characteristics of the chi-square distribution table. First of all, when we're looking at the chi-square distribution, right out of the gate we can see that it's a different shape. It is not that symmetrical shape where we have a central mean, median, and mode, where we have negative values to the left and positive values to the right. Looking at this, we can see that it's skewed to the right. We look at the lower axis here, we can see that we have all non-negative values, and that is because our chi-square distribution relates to variance, and variance is standard deviation squared. Anything squared, whether it begins being positive or negative, any number squared will always be a positive outcome. So we are only going to be looking at non-negative values here. When we start looking at the table itself, we can see that we are dealing with degrees of freedom, and that's very similar to the t distribution. Also, we're looking at the body of, in this case, it's chi-square values in the body. In the t distribution, it was t distribution, or t values in here. But our top row, in our t distribution, we had two top rows. One row dealt with the probability for a one-tailed test, and the other row dealt with the probability for a two-tailed test. With our chi-square distribution table, we only have one row of probabilities up here. So if you are doing a two-tailed test or doing a confidence interval, which is a two-tailed event, you're going to have to take whatever given probability you have for alpha, whatever your alpha will be, needs to be split between two tails, and you're going to have to calculate what those are. If you were doing a single-tailed test, a left-tailed test, you're going to have to look at each of these probabilities, and right out of the gate here you're going to notice this is a pretty high probability because our chi-square distribution is going to show, it provides probabilities to the right. It's reflecting probabilities, or the area to the right. Up until now, we've always been dealing with probabilities and significant critical values to the left. So we kind of have to switch gears here. So keep in mind that the probabilities up here are reflecting probabilities to the right of whatever our critical value is. So also looking across here, you're going to see that it starts out pretty high, 0.995, all the way down to 0.9. Then all of a sudden we drop to this 0.1. That's what I call the insignificant area in here has totally been deleted from this table because we're not dealing with that. These are the probabilities that we'd be dealing with when in our tails. So this from here over would be our left tail, and from here over to the right would be our right tail. So when we're looking at this value, these probabilities to the left, what I encourage students to do is calculate the complement of each of these values and just write its complement above it. So over here, for the complement to 0.995, we would be looking at alpha of 0.005. Complement to 0.990, we'd be looking at the alpha of 0.01. Here we'd have 0.025, here we'd have 0.05, and here we would have alpha of 0.1. That automatically tells you your alpha to the left, and that I think is more helpful than seeing these probabilities to the right in this portion of that chart. On this portion of the chart, it's set up just fine and it's ready to go. Okay, so now that we've had a review with that, let's practice finding some different values. So in this first problem here, we're not doing a hypothesis testing. We're just practicing finding critical values. Find the critical value chi-squared, or critical chi-squared value for a left-tailed test when n is equal to 11 and alpha is equal to 0.01. Now we need that 0.01 to be in the left tail, because this is we would be looking for a left-tailed, doing this for a left-tailed test. So that means we're going to have to look at the 0.99 column, because that 0.99, implies that we've got 0.99 area to the right, but our alpha needs to be 0.01 to the left. We're going to be looking at degrees of freedom of 10, so going back to our chi-squared table, we're going to go down here to degrees of freedom 10, and I'm going to use this column here, chi-squared 0.99, to come down to 2.558. That would be the critical value that would be associated with a chi-squared value of 0.990. That would be 0.99 area to the right, and we would have 0.09 in alpha to the left. So going back here, I kind of drew what the picture might look like, and I wrote in here and then shaded in where our rejection zone would be based on that critical value of 2.558, which was associated with this data here. Okay, on our next one, we're finding the critical chi-squared values for a two-tailed test when n is equal to 9 and our alpha is equal to 0.05. Now, a two-tailed test, we need to remember that alpha must be split in the two tails. So we're going to have to take alpha divided by 2, which would be 0.05 divided by 2. So we're going to have 0.025 in each tail. So we'd be looking at the column 0.975 as well as the column 0.025. That would be our chi-squared left and our chi-squared right. So going back to the table, I'm going to look down here at degrees of freedom 8, but I'm going across to right here, this third column in, is our chi-squared 0.975. So that would give us a chi-squared value of 2.18. That would be the critical value that would mark or identify, be the borderline for our left tail. Over here in our right tail, we're going to go to the column chi-squared 0.025, go down to the row for degrees of freedom of 8, we'd have 17.535. That would depict the critical value that would mark and identify where the rejection zone begins in our right tail. So going back and drawing the picture here, do the picture of our left tail, connected, and I labeled our chi-squared, and the left tail is 2.18. That would be the critical value for that left tail. Our critical value for our right tail is marked by 17.533 for chi-squared, the right tail. Okay, those were just practicing finding our critical values using the chi-squared table. Okay, doing our first hypothesis test. A dairy processing company claims that the variance of the amount of fat in whole milk processed by the company is no more than 0.25. You suspect this is wrong and find that a random sample of 41 milk containers has a variance of 0.27. At alpha 0.05, is there enough evidence to reject the company's claim? Assume the population is normally distributed. Okay, one thing that kind of jumps out to me here is, what the heck, I don't have any value here. Is this milligrams, grams? What are we measuring? So you need to keep in mind that it seems kind of strange that when you're given variance, that is some measure squared. Well, when you square a measure, that squaring the unit doesn't seem to make sense. So our value loses a unit. Units just don't make any sense. We don't say milligrams squared. Okay, so that's one thing. So variance will not have a measure, a unit measure. Okay, what is going on here is the processor, milk processor, is saying that the milk content in their product varies by no more than some amount. They say that it's the variance is 0.25. You think that it does vary more than that. So you're thinking the milk could be low, it could be high, you know, it's not consistent. So you're saying there's a higher measure of variance there. So you say the measure, you do a sample and find that we have a variance of 0.27. Now that's a little bit higher, but is it high enough to be significant? So that's what we're trying to find out in this test. Okay, so going back to the old standard, we have to set up our null and our alternative hypotheses. Our variance, which is sigma squared, is equal to, again, our null hypothesis always has the equal sign. This is what the company's claim is, 0.25. Okay, you're thinking it's greater than that. So where our alternative is going to be variance is greater than 0.25. Our confidence level is 0.95%. Our alpha is 0.05. This is a right tail test because it was greater than. Our sample had 41 samples in it. So our degrees of freedom is 40. we're going to go to the chi distribution, and we're going to find that the degrees of freedom given 40, and we're going to be looking at the chi squared 0.05. All of that's going to be in the right tail. So I'm going to go ahead and take a look at that. So I'm going to have, slide down here a bit, 0.05 column, that's the fourth in from the right, all the way down to our 40th row here for our 40 degrees of freedom, 55.758. So that's how we found that critical value chi-squared distribution. Okay, setting up our test statistic, we're going to be using this formula, n-1 times our sample standard deviation squared, or you can look at that as our sample variance divided by the population variance. Okay, so 40 times 0.27 over 0.25. So remember, your denominator is always going to be that population variance that you're testing. Do not square these because they are already squared. Variance is automatically squared, so you don't have to square these. It's just this is standard deviation squared, which standard deviation squared is sample variance, and this is population variance. So we calculate that all out, we get a test statistic of 43.2. So when I'm thinking about this, 43.2 compared to 55, we can know that 43.2 is not greater than 55, so we don't think it falls in the rejection zone, but we're going to draw out our picture and take a close look at this. Critical value is 55.758. We can see when we draw it on the picture, 43.2 does not fall in that. Our p-value we're going to have to get from the StatCrunch, and I'm also going to do confidence interval in StatCrunch. So when I go into StatCrunch, I'm going to hit Stats, and I need to go down to Variance Stats. I'm going to go over to one sample with summary. I need to put in my sample information. I'm going to try to, from my problem, I can see that my sample variance is 0.27, so I need to put in 0.27. And my sample size was 41. You put the sample size in, StatCrunch will calculate from that to get to the degrees of freedom. So you don't put in degrees of freedom, you put in sample size. We are doing hypothesis test. In this case, we are testing our null hypothesis was the claim that it's equal to 0.25, and we are saying that it's greater than that, so we need to change the sign. Okay, and then we want to hit compute, and we can see that our test statistic came out to be the 43 that we got, 43.2 that we got here, and our p-value is the 0.3362. Okay, so if you need to find an exact p-value, you're going to have to use StatCrunch. Okay, so I want to go back and do the confidence interval, so I'm going to click Edit, and I need to come down here and click the confidence interval. But remember, we were doing a right-tailed hypothesis test with an alpha of 0.05. So maintaining 0.05 in that right tail, the confidence interval that would guarantee that would be 0.9, giving, which would allow 0.05 in the right tail, 0.5 in the left tail of a confidence interval. So we're going to compute, and we'll find that our confidence interval is, I want to make sure that I talk about this, is 0.19 all the way up to 0.41. So in other words, what we're saying there is that the true population variance, based on this survey or sample, should fall somewhere between 0.19 and 0.41. And we look at our population variance that we're testing, 0.25 falls smack in the middle of that. So there is no way we can reject the null hypothesis when the null hypothesis parameter falls in our confidence interval. So all three of these methods, let me close this down, all three of these methods support that we will fail to reject the null hypothesis. There is not enough evidence to reject the company's claim. So in other words, even though this is our true sample variance came out to be somewhat higher, it is not high enough to be significantly significant that we could always assume that all containers would have a variance higher than the 0.25.